Since the structure of Hermitian function fields are a bit more precise, I want to explain Hermitian codes over a two example. So first, let me fix the finite field. So we choose is Q. And in order to construct algebraic geometric code over FQ square, we define F4 as F2 adjoining gamma. Gamma satisfies this inequality. And we define the Hermitian function field. If Q is 2, we define it as F4 adjoining X and Y, and X and Y satisfies the equality Y squared plus Y. Here this denotes the Q equal to XQ plus 1. So here we can also view this left-hand side as the trace of the function y. So in order to understand the rational places explicitly, the first place we consider is going to be O, or Q infinity. It is going to be common pole of X and Y. And for the other rational places, indeed, we can compute that for each gamma, trace of Y is going to be gamma cube. So that means if you consider the elements of F4 as 0, 1, gamma and gamma square, or gamma plus 1, trace of Y is equal to 0 means we want to find Y such that Y squared plus Y is equal to 0. And in this case, when we fix X as 0, indeed we can observe that the only options for Y is going to be 0 and 1. And similarly, if we check this equality for other elements gamma from F4, we can find the other possible options for Y's. Here, each time we take the trace as F4 over F2. Indeed, these solutions gives us the all possible options from alpha and beta. So that means for the X and Y coordinates. So that means for alpha and beta from F4, we get the coordinates of the places as 0, 0, 0, 1, 1 gamma, 1 gamma square, and gamma, 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 gamma square, gamma square, gamma, and gamma square, gamma square. So indeed, we can easily see that we have 8 rational places which are determined by these coordinates alpha and beta. And let me denote my from P1 to P8. And in order to construct a Hermitian code, let me also consider the Riemann space with R as 5. Indeed, we can observe that the functions y1, x, y, x square, and x times y forms the basis for this Riemann space. And we can define our Hermitian code as the evaluation of D. Here, D is defined as the sum of the pi's. So that means our linear code is of length 8. Moreover, we can give the explicit form of the generator matrix of our linear code, of our Hermitian code, because the evaluation of the constant function is going to be one vector, the vector 1. And if we evaluate, so these are going to be P1 up to P8. So for these evaluations, let me recall the fact that when we evaluate the function x at P alpha beta, we take the x coordinate, and when we evaluate the function y as the rational place P alpha beta, we get the y coordinate. So that means to evaluate the function, for instance, at P 0, 0 is going to be 0. P, so that means, sorry, this is going to be, let me denote it 1. And P, when we evaluate our function x at P2, its x coordinate is going to be 0. But for instance, if you evaluate at P5, its x coordinate is going to be gamma. And similarly, we can also do the same observation for the function y. For instance, if we evaluate it as P8, we take its y coordinate. But if we evaluate it at P2, we get 1. So indeed, by this observation, we can explicitly write the evaluations of these functions at given distinct rational places. Indeed, this evaluation map is also injective. To 6 for x and y, x and y, p alpha beta is going to be evaluation of x and evaluation of y. It's p alpha beta is going to be alpha times beta. So that means we can take the product of these two vectors. It's going to be 0, 0, 0. It's P for, it's going to be gamma. I'm sorry, I used a different notation. So, I mean, for the alpha, what I want to say is gamma. Sorry for the ambiguity. And if I don't make a calculation mistake, so for P4, we get gamma square. And at P5, we get gamma square. And at P6, we get gamma cube. So it's going to be, if gamma square is gamma plus 1, gamma cube, gamma square plus gamma. Gamma plus 1 is going to be 1. And it's 7 and 8, 1, and gamma. So these vectors are also going to be linearly independent in F4 to the 8. So it will form a generator matrix of the Hermitian code is of parameters 8 and dimension of length 8 and dimension 5. And for the minimum distance, we can use the theorem 2.2.2, and we can see that its minimum distance is at least 3. So maybe a homework which is supported by SageMath to check such a code is MDS or not.